My name is Jamika Marshall, and I am very pleased to serve as the Shadow the Scientist Coordinator. The STS initiative is housed under the Creating Equity in STEAM umbrella of programs, which is offered by a team at the University of California, Santa Cruz. In this session tonight, we have the privilege of shadowing the Shadow the Scientist founder, Raja GuhaThakurta from the University of California, Santa Cruz, Eric Peng of NOIRLab, and Elisa Toloba of the University of the Pacific, who are members of the Next Generation Virgo Cluster Survey Research Collaboration. They will be using the Keck Cosmic Web Imager and Reionization Mapper instruments on the Keck II 10-meter telescope to study the stellar dynamics, that is the motion of stars, and the chemical composition of an unusual class of galaxies known as ultra-diffuse galaxies, or UDGs. These are located about 50 million light years from us in the Virgo cluster of galaxies. Now, the twin Keck telescopes, one of which they'll be using this evening, are some of the world's most scientifically productive optical and infrared telescopes. Now, each of these telescopes weighs 300 tons and operates with nanometer precision. The telescope's primary mirrors are 10 meters in diameter and are each composed of 36 hexagonal segments that work in concert as a single piece of reflective glass. The Keck telescopes host a suite of state-of-the-art observing instruments and adaptive optic capabilities to collect and analyze astronomical data. And as I said at the beginning, the team is doing a bit of troubleshooting right now. So we are actually joined, Raja is here, but before we go back to Raja, we have a very special guest who I'd like to introduce, and this is Bryce Boland.
Thank you, Jamika. Hi, this is, sorry if I look, I have like crazy hair right now and just kind of relaxing at home right now. But yes, I am a postdoctoral researcher at Goddard Space Flight Center, which is in Greenbelt, Maryland. And the main thing that I focus on is small bodies of the solar system, like asteroids and comets. Let's see if I can show you here. If you can see it in my background, there's this, this comet, this kind of green looking comet here is called C2022E3, is one of the comets I discovered. And I don't know if you all remember, but last year this was like all over the news as the famous green comet. And it was kind of a surprise, but it got bright enough to where you could actually see it with the human eye. If you drove out and were in a dark enough site, you could maybe kind of see it. So I like studying things like this, like comets and asteroids. I think they're kind of like, the cute small animals, cats and raccoons of the solar system. Talking a little bit about my journey. I started out in astronomy as a graduate student, doing my master's at the University of Central Florida in Orlando, Florida, where I worked with Jan Fernandez and Joshua Caldwell on studying comets and rings of Saturn. And that eventually led to me working at the University of Hawaii in Honolulu. I was working with Robert Jedicke on Pan-STARRS observations of asteroids and comets. That's kind of where I started to become more involved in doing hands-on research and being involved in the discovery of comets. And then after that, I moved from Hawaii to France, again, all the way around the world again, where I was a PhD student at Nice Observatory. Nice is a smallish town on the southern coast of France, near the border of between France and Italy. And I was there for several years, and then I went to University of Washington for my first postdoc at the University in Seattle, where I was studying preparations for observations of asteroids with Rubin Observatory's legacy survey of space and time. It used to be called LSST, Large Synoptic Survey Telescope, but now it's called Rubin Observatory. And LSST is still kept around, but it means Legacy Survey of Space and Time instead of the Large Survey Synoptic Telescope. And then after going from the University of Washington, I moved to down the West Coast a bit to where I was working at Caltech in Pasadena, California, where I was at Palomar Observatory working on discovery of asteroids and comets. And that's when I found this green comet thing. And now I was there for several years, and now I'm at Goddard. What I'm doing with hopefully what I want to do with Shadow the Scientist is my work with the NASA Infrared Telescope Facility. That's part of the work that I'm doing at Goddard, which I'm studying asteroids that are called families. They're groups of asteroids that are related to each other by being collisional fragments. And they all come from a parent body. It's kind of like you have like a parent asteroid that breaks into many pieces, smaller pieces, and then the fragments themselves are called the daughter asteroids, or the children asteroids, and they're collisional fragments of this larger parent body asteroids. And so I'm trying to study how figure out ways of how these fragments are related to the parent body. So if y'all want to watch me in doing Shadow the Scientist, you'll see lots of asteroid and maybe some comet stuff. So I hope you'll like it.
Absolutely. We will be posting the links to Bryce's sessions shortly. So check back frequently on the STS website. And of course, if you are on our mailing list, you will get an email announcing his upcoming sessions. If you have questions or any comments for Bryce about his research, or even astronomy in general, please feel free to post those in the chat. Bryce, I have a question. Was this your first comet or your first discovery?
It was not the first comet I discovered, but I think it was the first one that got in the news.
Wow.
And so it was discovered in March of 2022, and I didn't really think anything of it because I had discovered comets before. I think I've discovered over 40 40 or so comets. And so I was like, yeah, it's exciting to discover a comet, but I'd already done it before, so I didn't really think anything of it. And then people started, there's a web group, which I encourage anyone to join if you're interested in studying asteroids and comets, or the topic of asteroids and comets. It's called the Minor Planet Discussion Group. It's a web forum and email list where people discuss, various enthusiasts around the world like to discuss asteroids and comets. And people on this web server, this web email list, started saying, oh, wow, this comet's actually going to come pretty close to the Earth in 2023 and could be as bright as magnitude 4 or magnitude 5. And the human eye can see, if you're in a really dark area, a really dark part of the place where you live, you can see down to magnitude 6 if you're really dark adapted, and or magnitude 5.5 or 6. So it became kind of in the reach of what's possible to do with the human eye. And so that made it pretty exciting, because I think the previous comet that was like this was Comet Neowise in 2020 during the pandemic. And I hope y'all got to see that. That one was pretty great as well.
That's amazing. No, I did not get a chance to see Neowise by eye, but I certainly was able to join some online groups that were looking at it live. It was cloudy. each time I could actually join. I don't know, did anyone in the chat, were you all able to see Comet Neowise? I know that was very much in the news during the pandemic, and it was one of those bright spots, pun intended, during that time. Or have any of you seen any comets yourself? I know I've seen a few comets, very, very faint comets on Mauna Kea, just with my own telescope setup kit with the guidance of some very keen observers. And it was absolutely thrilling to be looking at something that was just that close to us, actively moving in the sky, that I know in a few days or even a few hours wouldn't actually be visible. That has to be so thrilling, Bryce. And so you've discovered more than 40 comets. What about other bodies in our solar system?
Yeah, so the work that I did, so I've been in astronomy for roughly speaking about 12 years. But roughly half of that time I spent working on surveys that were dedicated to finding asteroids and comets. So the first one that I worked on was called Pan-STARRS when I was at the University of Hawaii. Pan-STARRS is a telescope that's based on Mount Haleakala. So everyone knows about the telescopes and observatory on Mauna Kea, but there's which is on the big island of Hawaii. But there's another observatory that is on Maui that is on Mount Haleakala, and it's about 9,000 feet in altitude above sea level, whereas Mauna Kea is like 13,000 feet or so. And but Mount Haleakala is still a great observing site, and so there are several telescopes there, including Pan-STARRS. So Pan-STARRS is a wide field survey. It's a 1.8 meter telescope, but it has a very wide field of view. It has a field of view that is more than a couple of degrees across. So it can cover large parts of the sky very well, very quickly. Comparatively, most cameras, telescopic cameras only cover a tiny fraction of a degree at a time. So having a camera that can cover degrees across the sky on a 1.8 meter telescope is a very powerful tool. So one of the objectives of this telescopes was to find asteroids. Pan-STARRS actually stands for, it's an acronym that it stands for Panchromatic Survey and Terrestrial Impact Alert Rapid Response System. So not only it's in the name that it was assigned to survey the night sky in multiple different wavelengths, it was also designed to find asteroids that could potentially impact the Earth. So with Pan-STARRS, I was kind of like an intern kind of person for several years. And my job on that was to help find asteroids and comets in the data taken by the telescope and verify them, usually by human eye. And I don't think I hold the record anymore. I'm sure someone has far surpassed this record. But when I left Pan-STARRS to go to France to do my PhD in 2014, I had submitted almost 2 million observations of asteroids and comets at that point, most of which were inspected by human eye, by my own eye. So I'd seen a lot of asteroids and comets. And I think the majority of those 2.8 million observations, they weren't unique objects. They were multiple observations of the same object. But the majority of them were main belt asteroids, but also near Earth asteroids. So main belt asteroids are asteroids that are located between the orbits of Mars and Jupiter, whereas near Earth asteroids are asteroids that come within about a third of a distance between the Earth and the Sun's worth. So they come within, it's roughly speaking, it's about 30 million miles. So asteroids that become within 30 million miles of the Earth, whether or not it's interior or exterior to the orbit of the Earth, are classified as near-Earth asteroids. And I think in that time period, we found something like several thousand near-Earth asteroids and some tens of thousands to maybe 100,000 main belt asteroids. And comets, I think we found around 100 comets, about a third of which were found by myself. But the most exciting solar system object that I found is the Green Comet. Is pretty cool. So that would be probably top 5. But the most exciting solar system object that I discovered was actually with the Zwicky Transit Facility at Palomar Mountain. So after I finished after I moved from Hawaii to France, about a decade later, I started working at Caltech at Palomar using the Palomar Mountain 48-inch telescope, which has which is called the Zwicky Transit Facility. And with that telescope, I found the very first asteroid that has an orbit that is entirely located inside the orbit of Venus. It's called an inner Venus asteroid. It now has an official name called Alochaxnum. I may be mispronouncing that, but it's a word in the San Luiseño language for daughter of Venus or Venus girl, and or Venus's girl. I think the name was chosen because in the morning, because this asteroid is only observable in the morning or the evening, and it's inside the orbit of Venus. So when you see the Venus in the night sky, it's usually sometime around sunset or sunrise. It's called the evening and morning star. So naming the first asteroid that is closer to the sun than Venus, that is something related to Venus, I think is appropriate. But I say it's exciting to me personally because when I started out in astronomy in 2012, 2011, 2012, I heard about these asteroids inside the orbit of Venus, and they were hypothetical. No one had ever seen one before, but people thought they could exist. And then almost 10 years later, I became the very first person to ever see one. So it was kind of a neat kind of goal I started out with, and I ended up being able to achieve that goal. So yeah, don't give up on your goals, I guess, is the moral of the story.
Bryce, that's absolutely amazing. Thank you for sharing, and congratulations. That's incredible, discovering the very first asteroid completely within the orbit of the planet Venus. Um, I'm very much looking forward to your upcoming Shadow of the Scientist sessions, and you all here with us this evening. If you're on our mailing list, you will definitely get that email as soon as we have those sessions scheduled. And if you are not on our mailing list, of course, you can check back on our Shadow of the Scientist website. As soon as those sessions are scheduled, you can register there. Certainly sounds like it's going to be exciting to tag along with Bryce as he continues his research of solar system objects. Thank you so much, Bryce. So Bryce will be here throughout the session. If you have any questions, feel free to put those in the chat. And now we can turn to this evening's observing team. We have with us the Shadow of the Scientist founder, Raja GuhaThakurta, from the University of California, Santa Cruz, as well as his colleague, Eric Peng of NOIRLab. And I believe we'll also have Elisa Toloba. They are members of the Next Generation Virgo Cluster Survey Research Collaboration. And tonight, they are using the Keck II telescope to study UDGs, these very interesting ultra-diffuse galaxies. So we can head over to you, Raja.
Thanks, Jamika. I was going to say that Elisa's going to join in hopefully in a couple of minutes, and then hopefully even Greg Dortman, our support astronomer, and Tony, our observing assistant. So they have the STS Zoom link, but welcome everyone. Many familiar faces, Rob, Yael, let's see, Yash. Yash is a student in one of my classes right now. Stephen, we're about to start working together. Stephen's at UC Merced. Hi. Let's see. What was I going to say? Eric, did you want to share your screen? Well, I should let you introduce yourself, Eric, and then if you wanted to share your screen, that would be terrific.
Yeah, sure. Hi, I'm Eric Peng. I'm an astronomer, staff astronomer at the NSF's National Optical Infrared Astrophysics Laboratory. And that is essentially the national ground-based observatory. And I'm observing with Raja and Elisa and others tonight on this ultra-diffuse galaxy program. I think Elisa just joined us.
Hey, Elisa.
And so, yeah, we've it's a little bit of a hectic part of the night because our main target has not yet risen, and it's not yet high enough for us to observe. So we're observing a bunch of calibration targets and trying to figure out exactly how to get the telescope to do what we wanted to do in this case. So we're doing a lot of sort of short exposures and then having to adjust quickly. If you had joined later in the night, once we get our main target on, we're just going to stare at it for 6 hours, and so there's plenty of time to I don't know, to do other stuff. And okay, I guess am I admitting people here?
No,
Okay.
I'm doing it. And actually,
I'm doing it. If you'll I got it. Thanks.
Okay.
Any of us can.
And so, yeah, so I guess Elisa's here and Greg's here, so maybe you guys want to introduce yourselves.
Okay, so I can start. I am a professor at the University of the Pacific in California. It's located in Stockton. I study galaxy formation and evolution, focusing on low surface brightness galaxies and dwarf galaxies. So what we believe is the building blocks of larger galaxies. And these ultra-diffuse galaxies that we are observing tonight, they are particularly exciting because we just discovered that these may be like the galaxies with the largest amount of dark matter ever observed in a galaxy. So we are trying to confirm if that is the case, because if that is the case, then we don't understand anything about galaxy formation, basically. So then we will have to revisit our knowledge of how dark matter plays a role in galaxy formation. And yeah, so we are trying to confirm these results that we got with the Keck telescope during observations for it was from 2017 to 2021 using the Keck telescope. So we did the observations. It took a very long time. We got the data and we got this very puzzling result, and we are following up with a new instrument that is allowing us to do the same experiment, but from a different perspective. Yeah.
CCD readout complete.
That's
Hi,
only our
everybody.
first exposure. We still have another one, so it's okay.
All right, great. Hi, everybody. I'm Greg Dortman. I'm the staff astronomer here at Keck Observatory. So my role is to make sure that the scientists have all the tools they need and things are working properly so that they can get the data that they're aiming to get tonight. So our goal is to facilitate their observing in every way possible. And that's a really nice thing for me, because I get to see some really excellent science coming through here at Keck Observatory. I get to play a role in optimizing that science. So it's very exciting for me to be able to be in this role. I've been at the observatory 13 years now, so I've seen a lot of instruments come and we haven't retired any yet, but we keep adding more instruments. And so this one we're using tonight is now a complete instrument. It started out with just a blue side only, and now we have the red side as well, has been added as of about 2 years ago. So we have the full complete red and blue coverage now that the spectrograph was designed to provide. So this is it's been exciting to see this instrument come to its full capabilities now.
I wanted to see if Tony is on here, Greg. If and when Tony is able to get on, we'll certainly have him introduce himself. I wanted to say that
Yeah, I see Tony has his laptop open, so hopefully he's going to be connecting soon.
okay, while we're waiting for him, I wanted to say that there are many amazing human connections here. Jamaica and I met in Hawaii through one of my former students, Brian Lemont, who was at Santa Cruz as an undergraduate, is now working in Hawaii. That's how Jamaica and I got connected. Greg, you and I met at Keck. My first night ever on the Keck telescope was on the 16th of September, 1995. I have it marked on my calendar. It's coming up on 29 years. This September, it'll be 29 years. My first night on the Keck II telescope, which is the telescope we are using now, was a couple of years later, because Keck II wasn't operational until, I think, 96. So it was October 2nd, 96 was, it wasn't Keck II started in 96? General operations.
That sounds right. I think that sounds right. 1993 was Keck I first light.
Right, nine.
So that sounds about right.
I joined UC Santa Cruz year after that, 94, but I didn't get on the Keck telescope until 95 September. My very first Keck proposal was turned down. That would have been for 95A, and I didn't get time in 95A, but 95B, it was 16th September. And I know I was on Keck II the second night of Keck II operation. General operation started on October 1st of 1996, and everything was breaking. The mirrors wanted to be 36 different mirrors and not part of one. So it was very exciting, the wrong sort of excitement. Elisa and I have worked together for a while. Elisa was a postdoc at UC Santa Cruz. And Elisa, you didn't say this, but you were a student in Spain before that, in Madrid. And Eric and I go a really, really long way back, right? Eric, 1993? 2? 3. So we go back as far back as the Keck I telescope then.
Yeah.
That was Princeton. Eric's undergraduate studies and my postdoctoral studies coincided. So anyway, there are a lot of human connections that are.
Exposure complete.
Okay, we are about to have to make a decision on something.
Okay, so.
So going to while we do this, I'm just going to share. This is what we're looking at right now.
Wow.
This is the globular cluster NGC 2419. It's not actually
Complete.
our main target. It's a calibration source. So I think what we should do, Lisa, is I think we should do the sky exposure now.
Blank sky?
Huh?
Blank sky?
Yes, so we're right now we're observing the center of this thing. You can ignore that green spike, because that's not actually there. That's just the image that was
Readout
taken.
complete.
And I think we should
CC
move.
readout complete.
Do you want the Sky 1 position?
Oh, we don't have a sky position for this
We don't
one.
have a sky position for
Oh, you
this.
don't. Okay. Gotcha.
Yeah. Yeah, I realized that we should probably have had one. Well, there are a lot
But we
of
could have Tony try to help us find a blank area that's, maybe an arc minute or so away.
Yeah, I was gonna move just like 10 arc minutes to the east and then
Okay. Sure.
yeah.
And I assume you wouldn't drift the sky.
We're not drifting the sky. We're not drifting this one either, actually. Sorry.
I see.
I can see the stars, individual stars. No,
That's amazing.
I think so. We have that. Oh. Is that gonna be a problem?
No, you can co-add them.
10 arc minutes.
Right, seeing individual stars wouldn't be a problem in the globular cluster, right? I assume you'll just co-add everything. All the spaxels. So while Eric and Elisa are doing this, the instrument we're using today is something called an integral field unit. It's actually two instruments. It's two instruments with something called a dichroic. A dichroic is something that takes a beam of light and splits it into two parts. Light longer than some wavelength goes one way and light shorter goes another way. Sorry, Eric and Elisa, it's all yours.
Great, thanks. I don't. Yeah, make sure there's some like star there. Yeah. Okay. You did it already? Okay. Looks pretty clear.
And I guess if there is a star in any of the spaxels, you just ignore them. Is that how it will work for sky subtraction?
Yeah, let's repeat the same exact exposure sequence as last time. Yeah. Oh wait, so we're back in KCWI, right? Yeah. Right. Okay. So yeah. Sky. Oh, that's a good idea. I think so. Just change the view for our audience here. Okay, so now, all right. Oh, you already, I just started the red side. Did you start the blue side already? Okay. All right. Okay, good. We got another 10 minutes now.
So for the globular cluster and the sky spectrum, there's no drift going on, right?
So we did not, we did one drift, but then we decided just to do a single pointed observation of the cluster center without drifting. That was the last one.
Mhm.
And then this one is just sky and there's no drift on the sky.
You don't drift. And in the sky, if let's say there's an occasional galaxy or star, those
Okay.
spaxels can be excluded from the integrated sky spectrum, I assume.
Yeah, right. Because we don't really care so much about there being a spatially varying sky, like, we'll subtract
Exactly.
it out, but we're really just going to sum it all up in the end anyway.
Yeah. And Jamika, your question was, what is drifting? In general, let me see if I can describe this. So this instrument, first of all, light comes down from the focused light from the telescope comes in, and it gets split by something called a dichroic into two parts. Long wavelength light goes one way, short wavelength light goes one way. You can think of it as blue and red light. Blue light goes into an instrument called KCWI. Red light goes into an instrument called KCRM. They are both IFUs, integral field units. What they do is you can think of them as taking not single images, but a set of images at different wavelengths, but many different wavelengths and simultaneously. So that's one way of thinking of KCWI and KCRM. They create data cubes, an image in each of, I guess, thousands or hundreds of wavelengths, thousands, right, of wavelengths. So in a 2D image, X and Y on the sky, but in each of 1,000 contiguous wavelengths. So another way of thinking of it is that each point in the sky, it creates a spectrum. So we are going to be studying galaxies in the Virgo cluster, and what we're trying to create now are templates. That is, spectra of systems of stars that are notionally similar to the galaxies we're going to study. Notionally similar meaning in terms of the mix of stars. Obviously, the system we're going to study and the system we're going to study during the night when Virgo rises, those galaxies are moving at a certain speed. The amount of dark matter in them, the amount by which stars are rattling around in those galaxies is different from this particular globular cluster. This globular cluster, stars are hardly rattling around in them, but the mix of stars is notionally similar. So we want to collect a spectrum from this globular cluster and then apply certain transformations to the spectrum until it matches our science spectrum. Two kinds of transformations. One is we Doppler shift this globular cluster spectrum, because this globular cluster is pretty much at zero velocity, but we Doppler shift it to match the spectrum of each science galaxy in Virgo. But we also broaden, smear out the spectrum to mimic the effect of Doppler broadening, to mimic the effect of the collective motion of stars, spread in the motion of stars. And it's like applying a Gaussian blur to the spectrum of the globular cluster until it best matches the science spectrum. And in this way, we measure the mean velocity and dispersion of the science target using this globular cluster spectrum as a reference spectrum. Now, this is happening simultaneously in these two instruments, KCWI and KCRM. Each one of these, one produces a blue spectrum, one produces a red spectrum. Now, what is drifting? Initially we thought, okay, if we just take a IFU observation of the globular cluster, some pixels, and these pixels are called spaxels because they're spatial pixels as opposed to spectral pixels. So that's why they're called spaxels. Some spaxels will capture the light of bright stars in the globular clusters. In the globular cluster, some spaxels will capture the light of faint stars, and some.
Complete.
You guys need to do something, or is it going to be a second exposure?
There's going to be a second exposure, so.
Okay. Some spaxels happen to be in the spaces between stars, so they're not capturing very much light at all. They're getting telluric spectrum, Earth's glow, but very little astrophysical light.
CCD readout complete.
The advantage of drifting is during the exposure, if you allow the telescope to drift, then you can sweep across the globular cluster during the exposure and capture light from more of it and average over stars better. That's the one of the notions of drifting. That's one of the reasons why one might want to drift. Normally, you point, you take a spectrum, you basically lock on while you're taking a spectrum. In this case, drifting might be an advantage. Now, what Eric is showing here is super interesting because what you're seeing is a set of spectra, not one, but multiple spectra. And each one of those corresponds to a row of pixels. Each of these bands is a 2D spectrum, and a set of 2D spectra gives you a 3D spectrum. That's what I meant by a data cube. Right, Eric, each of these is a 2D spectrum, right? That we're looking at each of these bands.
That's right. So each one of these, each row here, where you see these lines, that line is an image of a slice of the sky, or traditionally it'd be a slit. But then imagine if you have a rectangular field, and it's just divided up into slices, and each slice is then moved through optics to be stacked one on top of each other. And then each slice is dispersed out into this spectrum. And the bright lines you're seeing here are lines from our atmosphere, actually emission lines from our atmosphere.
This is the blank sky spectrum right here we're looking at.
This is the blank sky spectrum.
And you see spectacular cosmic rays. I guess this is the KCRM side, right?
This KCRM.
This is the red side. And
Quite a few in the red.
What does the blue side look like? Because you said it's a very thick CCD. So these high energy rays come through. The thicker the piece of silicon, the more its stopping power for the greater its stopping power from high energy particles, and those deposit energy that looks indistinguishable from light releasing electrons in the silicon. That's what these bizarre.
I've never used a CCD like this. I've never seen cosmic rays this
scary. Yeah, this scary.
Yeah, they're not there. They've got some structure to them, and you see them in this abundance.
Yeah.
It's I mean that's 5 minutes.
And that's a lot of cosmic rays in one location. They don't seem uniformly distributed across the array, but that might be just stochastic. What does KCWI look like in this, the blue side? Is there a similar image?
It looks like
pretty clean. I think I can see one cosmic ray in the blue side.
Oh wow, lovely. And there are very few night sky lines also on the blue side, I guess.
Yeah, so like I see something down here.
some of these.
I see a dark band on the. I see an absorption band. Is that telluric absorption we're seeing, or is that solar lines? The night sky still bright. That looks like something from the sun.
There's a little moon out.
Ah, I bet that's what it is.
Yeah, that's what they were.
I think we can
Maybe
see
the-
H beta and the magnesium triplet. I can see the magnesium triplet on the right.
Yeah.
And that must be H beta on the.
Oh yeah.
So the sunlight reflecting off the moon, and so what we're seeing is a solar spectrum. That must be H beta, that strong line. That's absorption of hydrogen from level 2 to level 4. So what's the wavelength coverage of the blue side roughly?
It's H beta to magnesium.
Oh, so that's exactly what we're seeing. H beta to magnesium. And the red side, it's covering calcium triplet, it looks like.
Yeah.
Exposure complete.
So there's a gap in the spectral coverage then between H alpha and about 8,000.
Right.
Sorry, between
This
magnesium.
is the high dispersion
I
rate.
see. So there'll be no H alpha, for example, right, in the spectrum. Okay. Are there any other lines in the red other than the calcium triplet, or?
No, I don't think so.
So sodium doublet at 8200 going to be in the range? No.
Sorry, the what?
The sodium doublet at 8200,
I
8198.
don't know if we're getting that. Let's see.
Yes, we may
Exposure.
the limit on the blue side is gonna be something like 8200, something like that.
Yeah.
Oh, on the blue end of the red side. Okay. You know
Yes.
what? 8200 is only strong in main sequence stars and M dwarfs. And of course, the
CCD
light is
readout
dominated by L
complete.
giants. You're not going to see it.
Okay, so this is the
Oh, beautiful.
next exposure.
Wow, it looks so different.
So what are we doing now?
I think we go to another star.
CCD
I think
readout complete.
Like a standard star.
I think we just do, because right now it's it's pretty much top of the hour. We probably have another half hour until we go to Virgo, or maybe a little bit less.
Let me see.
So what do you think? Should we just do some stars?
Okay.
Because we only
Right
got
now, Virgo looks like Virgo's at about 2.16 air masses now.
okay.
Yeah,
Is-
way too. Okay.
Is the elevation limit still 40 degrees?
Yeah, and unfortunately in the east, we vignette when we get below 40 degrees elevation. So right now, Virgo is at, let's see, what's the elevation would be, 28 degrees at the moment. So
So
you
we
want to
go
wait,
to our
you want to wait a little longer before, so it can rise into the dome slit.
so
Hmm,
let's
so-
go to the next template then.
Yeah, let's do that.
Okay, let me
I mean, I
then
think
highlight this.
we've gotten, we've got some exposures in this, but probably 10 minutes wasn't quite long enough, but I don't know if we want to sit on it. That's the thing. I mean, our other option is just to sit on this one, but then we don't have any other stars.
But you think that this is not good enough?
Oh. Sorry. I got you coming in through two things here. Yeah. Yeah, let's do a few stars. So we kind of like hedge our bets on this.
Why is this sky spectrum looking so different? Oh, is that because the moon is set?
Adjust it yourself. Do that now. Guider.
Should we take a guided image?
Sure.
Let's go. So, do we want to center a little bit more, or we're okay? We're gonna do drift scan.
We're gonna drift again, right? So yeah, let's center it up.
Sorry, what was that? I didn't hear you, Eric.
Oh, we're just gonna. Oops. Sorry.
Okay, I can hear you now. It's weird because the mute, it says you're muted, but I could actually hear you.
I think you can hear me because it's through Elisa's other Zoom, but now I've unmuted here. Yeah, we're just gonna set her up here a little bit.
Okay.
So are you gonna?
You want me to do it? I can do it. Let's move it up
No, to the right, right?
and then to the right. Say one to the right. Take another guider image.
Okay.
That looks pretty good.
Yeah.
Okay.
Okay.
KCWI. Okay, we're in position and guiding here.
Okay. Now
The drift scan 20.
drift
This
scan.
one is way fainter.
This
2
one's
magnitudes fainter.
2 magnitudes fainter.
Yeah.
So what was our? So we're
We were
doing
doing 4 seconds.
we're doing 4 seconds. Well,
So this is actually gonna help us.
yeah. Should we do 10? Because the other one we saturated a little bit on one of the slices, didn't we?
So should we do 20, 10?
20 arc seconds and then 10 10 seconds. How bright is this one?
It's 7.7.
Ooh, yeah, it's still pretty bright though. And what was
So
the
10 seconds or less
huh?
for the drift scan. 20 arc seconds, 10 seconds.
Yeah, let's do that. Okay, so
Let's get it ready.
okay, wait. I gotta get my stopwatch out. All right. Let me know when you're ready to start.
So I don't have to do anything in control 1, right? So
You don't. You just have to set the drift scan command going.
okay. So whenever you're ready, I will let you know.
You let me know when you tell me when you're going.
You're ready?
Mm-hmm.
Okay, go.
All right. This is a very low-tech solution to this problem where I have to hit now. I gotta start the exposure so that we can sync up these things together. These two are going at the same time. All right. Not
This is the
bad.
very first semester that KCRM has been on the telescope.
Yeah.
Exposure complete.
Okay, so both of them at the same time. You can see the blue side and the red side are totally independent, which is why we have to synchronize them in this kind of manual way. We're doing this. Presumably in the future, it'll be more automated.
This is the first semester of KCRM being on Sky.
The readout complete.
Yeah. Ooh, not bad.
Oh, that's beautiful. Wow. Wow.
Yeah, we got them on. Okay, let's take
This is the red side. That's the
this is the
calcium
red
triplet.
side.
That's the calcium triplet right there.
Oh. What did I hear? It is.
CCD readout complete.
Okay.
Wow.
Count
Wow.
level looks not too bad.
Are you able to do horizontal cuts, Eric?
Yeah, probably.
You see the calcium triplet. There we go. There we go. That's the calcium
three
triplet.
lines
1, 2,
here.
3.
Yeah. Go to the blue side. The blue side looks okay.
Oh, it's got lots of lines.
It looks okay.
Beautiful.
Yes.
All right. let's move on to the next star.
Okay, so let's go.
What a beautiful instrument this is. Really spectacular.
Tony, we are moving to number 2.
Okay, yeah, I see it highlighted. I'll start moving.
Thank you.
I have a quick question, Eric and Elisa. This is a single bright star.
Yeah.
But the reason we are seeing it in multiple 2D spectra is because of the shape of the PSF. It spills over into multiple slices.
It's because we drifted across.
Oh, you drifted. Okay, you drifted. I see. If you hadn't drifted, we would only see it in one of the 2D spectra, or one or two of the 2D spectra.
Right. Yep. Or you'd
Okay.
see it in a few adjacent ones.
Yeah, I guess the PSF would just split it.
Yeah. But this is because this drift happened. So
I
because we
see.
wanted to try to get it across the slices. We don't have to get them across all of them, but we wanted to at least move it across a few.
And you always drift in the perpendicular to the slices, I guess.
Perpendicular to the slice, yeah.
Oh. This really feels like a 21st century
Okay.
instrument.
Right, so east-west, huh? Yeah.
Yeah, east-west. I should point out, one of the positive things about the pandemic was that it got us fully remotely connected to our observing community, so that now people can observe from their homes without even having to come into a university, much less fly to Hawaii, which used to be the case before pandemic. We had about half of our observers would actually fly out here to observe. So now that the cat's out of the bag and we've got the remote observing dialed in pretty well, people can observe from anywhere in the world with a computer.
So this pajama mode is what really got Shadow the Scientist started. So
Another positive benefit.
Yeah, because we said all of a sudden the playing field is level. The scientists are not at the telescope. They're not at the observatory. They're at home. So other people can also be at home. It's not quite a level playing field because the scientists can control the instrument. The eavesdroppers can't. But the view, at least, is very similar. Not the control, but the view.
Yeah, it's been really helpful for students learning how to use the instruments. Because they can easily jump on and just eavesdrop without, any problems at any hour.
What is the dark patch we're seeing in the magic window? Is that the bright star, or is that something else?
The hole in the middle?
Yeah.
Yeah, that's the light that goes to KCWI.
Oh, I see. That's why we're not seeing the sky. Okay.
And that's why we call it an annular guider. So we can only see stars that are around the annulus of the field of view.
But it seems like
when we had just KCWI, we were actually using the red light to guide on. And so we were on axis guiding.
Got you.
Because the red light was not being used, but now we're using the red light in the KCRM instrument. So we have to guide off axis.
Hey guys, I've got your star set up here. I don't know if you want to do any more adjustment to it with the guider. So just leave that to you.
Okay. Let's take the guided image.
All right, yeah, we'll do that. Oh, did you already do that? Oh, here it is. Move it up. Okay. Left. Okay, we're good. I think we can, yep. What magnitude is this? Okay, so similar to the last one. Let's just do the same thing. Yep. Yep. 10 seconds. Just let me know when you're ready to go. Pretty good. 16.
Exposure complete.
These 16 seconds is the delay between when Elisa starts the movement of the telescope and when I hit expose on the red side. The script she's running automatically controls the blue side, but I'm trying to sync the red side up with the blue side so we get the same exposure. Which is
CCD readout complete.
oh, looks pretty good. Okay, in terms of counts, should be okay.
CCD readout complete.
Okay, how's the blue side looking? I'm just looking at the red side. Okay. Should we go do the next star? Yeah. Let's pick one that's, I don't know if there's one that's closer. We don't have to, it's such a huge slew, but to where we are now. I guess they're all kind of the same. Well, are we good? Are we doing them in a, are we just done 1, 2, 3? Is that what we've done so far? Okay. Yeah. To what? Sorry. Oh, is that something we want to avoid or? What if we went to the next one, the fifth, number 5, because that one is maybe. Let's go there. Mm-hmm. Okay, and that's just because the latitude of Mauna Kea of Hawaii is 19. Okay. So this one maybe we do, it's like 2 magnitudes fainter, right? So, or magnitude and a half. And the number of counts we got in the last one was, could be more. Should we do, what we doing, 10 seconds last time? What are you gonna do, 60 seconds? Okay. Oh, I did. Yeah, it did move. So I think we're good. I think we're not going to change anything. So yeah, let's do 60. Okay. Whenever you're ready, Lisa. Yeah.
What is
Fix
this a spectrum of, Eric?
the drift scan, you mean?
No, I mean the spectrum that says projection
Which one? Sorry.
on the, the window. There are these two windows on the yeah, that window. Is that just a cut across the star?
That was a horizontal cut off of one of these, but I don't know what part of the spectrum I was in.
No problem. No worries. Okay.
Yeah, Lisa, I don't know if we should, I don't know how we fix it. So if it can do it at the same time, that would be convenient. Do the red side. I think Greg was suggesting maybe just a separate script that just controls that, but right, yes. Hmm. Mm-hmm.
CCD readout complete.
Oh, you can see the
Yeah.
calcium triplet again.
Yeah. It didn't occur to us that, we were still thinking, we knew of course that KCRM was there, but until you're actually using it, you don't think, all right, they're two totally separate
CCD
things.
readout complete.
I guess I'm used to something like this for the CAS spectrograph, which is a double spectrograph, and you have to start the exposure separately, and there's no, it's like two separate instruments. Wow.
There's plenty of signal there. Blue side looks good. Whoa, yeah. All right. So I'm just keeping an eye on the time here. Virgo is now above 2 hour masses. Do we want to, I don't know if we're above 40 degrees yet.
Is there a facsum? Oh, but that won't tell you.
It's NGVS UDG 19. Okay. All right. Well, we can do one more of these. Well, should we go to I guess there's only one more star on this list, right? Yeah, it'll take us to the North Wrap, but looks like we've still got to wait a little bit anyway. So that's number 4. Yeah, okay. Mm-hmm. Okay.
Hmm. Hmm. Hmm.
All right. Let's move this over a bit. All right, take. There you go. Maybe a little more. All right. It looks okay. Yep. So this one's the same brightness as the last one. So I guess we'll just do the same exposure time then. Yeah. Okay. Hold on a sec here. All right. Let me know when you're going. No, it's kind of crazy. We should put this in the paper. Yeah. Yeah.
What are you thinking of putting in the paper,
I-
Eric?
Of course, all this like dinging and everything, and then us talking, and I missed the 16-second mark. It's all right. Should be okay. Does the STS Zoom ask everybody to admit a new person when someone joins? Because it asks me for some reason.
It asks
can-
you because you're also a co-host, but I'm admitting everyone based on the registration list.
Okay, yeah.
Jamaica was asking what the to talk about the calcium triplet. It's 3 absorption lines that are produced by.
Exposure complete.
Oops, do you guys need to do
Exposure
something?
complete.
Yeah, well, we just have to take a look once it's run out.
Okay. I'll
Um,
pause.
CCD readout complete.
okay. Okay. That's fine.
CCD readout
Oops.
complete.
How's the blue side? Okay, it's excellent. Okay, so we still have a bit of time, right? Before we go to Virgo. If we so although I asked Dave Sand for a target and they couldn't, the one they found was not going to be high enough right now. It was actually another UDG. But he did give me a supernova if we were
We may as well get it.
Huh?
I emailed Mika and Dennis. I didn't hear back from Dennis, but Mika texted me to say she has an exam tomorrow and she's going to be working late today, so she wasn't able to, help with the smudges target.
Right.
Let's get the supernova.
Let's get the supernova for him. Okay, so okay, so Tony, can I read out some coordinates to you? Okay. So RA is 10, 21, 49.7, and is plus 56, 55, 40.46. Yes. Yeah, it's SN 2024 BCH. B as in boy. Great. Yes. Set an LST around 9, so we've got about 15 minutes. Okay, sure. I have no idea how bright this thing's gonna be. Because it's faded a bit, quite a bit, probably.
I think I can, I mean, unless this is some very, very bright other object in this galaxy, I'm almost certain that we're right on the supernova.
Okay. Should I take a guider
So-
image here then?
Yeah. And if you have trouble seeing, making something out with the guider, if you change the guider cut, which is underneath the image here, and underneath you see the bar that shows the width of 60 arc seconds. Underneath that, you should see where it says cut. If you change that to min max, you'll see exactly what I'm talking about. It becomes much more obvious.
Yeah.
Oh, it might be at the top. Yeah, I'm sorry. I might have a different GUI than you.
Okay.
I think we are on it, right?
I think there's something, I mean, this is the image I just took, right? So there's something right in the middle.
Galaxy to the north of this position, or north east.
So this is, there's a host galaxy to this supernova. So,
Yeah.
You can see the galaxy here.
oh yeah, in the annulus.
But it looks like it's the supernova.
Yeah.
Wow, that's extremely bright. Wow.
So it's in the guider pointing reference, pointing origin right now?
Oh, here it is. Yeah.
Yeah.
That's super cool. And this is supernovae get as bright as the host galaxy themselves, so that's
It's
pretty
pretty
exciting.
well centered to me, maybe not exact, so I don't know if you want to center it up.
I think it's probably good enough. So
Okay. Send it over to KCWI.
yeah. What I don't know is now, so how bright is that? Probably. Where am I here?
Yeah, that's a good question. I don't know.
Well, I think
You are efficient whenever you're ready.
we, how much time do we have before we want to be moving again? So
10 minutes.
10 minutes, yeah. So let's just do the same thing. We'll do 625 here, and then 2 300s on the red side. All right, so should we go, Lisa?
Let's go.
All right, let's go.
I guess when you're taking a spectrum of a point source like a supernova with an IFU, it doesn't matter where within the field of view it is, as long as it's in
No.
the field of view.
But IFUs, or at least small IFUs, are nice for rapid follow-up because you can just go right to it and expose.
Okay. So we have like 10 minutes and then we move to Virgo.
Yep.
Okay.
In the blue, in KCWI and KCRM, I noticed that there's a set of 2D spectra, sort of two sets of 2D spectra with a gap in between. Why is that?
I don't know if it's two halves of the IFU. Greg,
It's
do
just-
you have a?
Yeah, it's just the way the slices are oriented. They're the bottom slices are arranged on the bottom half. There's I don't know why there's this gap in the middle, but it's just the way the layout is arranged. But yeah, each one there's this 12 slices on top and 12 on the bottom.
I see.
Well, so far pretty smooth, and I don't think that I have had a, such a good weather in like years.
Bite your tongue.
It's okay. The seeing's not so good, but we don't need the we don't need the seeing.
So this supernova must have been discovered recently, Jamaica, because it's got a 2024 number.
It was discovered in January, which is why I'm surprised it's still quite bright.
Yeah, so I wonder what kind of supernova this is, if it's still that bright, unless it was discovered very early stages. These things stay bright for a few weeks, right?
It's a type 2 supernova.
So this is like the cobalt, isn't the cobalt half-life the sort of width of the peak? What is its ID? 2024B
CH,
ECH.
which is crazy that by January 29th,
Through the
Oh,
alphabet.
okay, end of January.
Running through the alphabet.
you're already like, yeah.
It's crazy because I remember, I mean, in fact, I was teaching my students in class today about 1993J, a supernova. The 10th supernova of that year was discovered in the fall. I remember we wouldn't get through the alphabet. And now with so many Assassin and so many other ZTF, yeah, you get through the alphabet 3 times in a month. That's crazy. But what does that mean? So is it really 26 cubed? Can't be that many supernovae in a month. Is that what it means to go through the alphabet 3 times?
Times 3.
Times 3, not cubed.
No.
I see. I see. So you go. Wait, I don't understand that. Why is the first letter B? Shouldn't that, I mean, I'm trying to wrap my head around the naming scheme. Eric, do you understand the supernova naming scheme?
I thought I did, and then you got me thinking about it. And now I'm not so sure.
Exposure complete.
It must be 26 squared times 2, because it's the second character is a B now. Oh, the first characters are B. So we've used up all the A's, which is 26 squared.
CCD readout complete.
Oh, here's the supernova.
According to the Wikipedia, supernova designations, initially it says year followed by one letter, then it says two letters, then it says three. So I think we're up to the point where we need three letters to discover all of the, to name all the supernova discovered in a year.
Wow.
Then it becomes BDA, BDB, and so on.
Yep, it must be that, right?
That's
So this is BCH.
And it was discovered in January 29th.
So we should be able to calculate how many were discovered from January 1st to January 29th from the letters BCH.
What, so the first one is AAA?
I guess so. So I think it's 26 squared plus, it's not quite 2 times 26 squared, because 2 times 26 squared would be BZZ.
I think in base 26 is what you gotta do.
That's effectively what it is, right? And that's
Yeah,
exactly what
It's
it
base
is.
26.
But the second character is a 2 and the third character is a 3.
I calculated this right. It's the 1438th supernova discovered in 2024.
On the 29th of January.
Yeah.
I'm getting a different number.
Exposure complete.
You said BCH, right?
Yeah.
I'm getting 736.
Exposure complete.
Shouldn't it be the BCH? So the B should be 2 times 26 squared. The C should
No.
be 3.
So it's 1 times 26 squared because it hasn't finished, it hasn't exhausted the B's yet. It's exhausted all the A's.
Okay. Yeah.
CCD readout complete.
Okay. Here we
CCD
are.
readout complete.
It's a very useful calculation as people can tell.
All right. Shall we move to Virgo? All this delay. Yep. Sounds good. That's fine. Yeah, I think so. And it's larger than the KCWI field of view, so it really doesn't matter what PA we choose. Okay.
I wonder though, so we've been slewing all around. I wonder if maybe you should do a full perimeter check. Check if there's anything new. Yeah, see if there's.
So what do you guys think this oil is from? Hmm.
Wait, there's an oil leak?
Hmm. Okay. Yeah. Yeah, we were moving at 10 arc seconds and then going in 20 and then going 20. Right? Because assuming that the target's centered in the field of view, then you go half and then you do the full field. Yeah. Yeah, so it would move 10 arc seconds and then it would start exposing and then it would drift 20 across the across the slicer. Nope. Our basic plan is going to be object, sky, object. And then, so we'll do whatever, I guess you said 13, 20 seconds. And then, what, what was it again? 300. Yeah, 300 in the red. Yeah. And then we'll do that on target. We'll go off to the sky position, the sky, I guess sky 1, and then come back and do that twice. And then go repeat until the target, until either twilight comes or the target sets. I can't remember which happens first. So with the 40-degree limit, we actually may lose the target. What, 40? Yeah, okay. Oh, we're not gonna see the target. I'm pretty sure. Yeah. Mm-hmm. 1320, yeah. I guess, I mean, okay, and they were doing 4 exposures of 300, right? Yeah, you go ahead. Let's go. Okay, so now we're pretty much pointed at our target for the night. And we're going to observe it for roughly 22 minutes. And then we're going to go off to a blank part of the sky, not too far away, so we can get a measure of what the background is, because this thing is really faint. It's much fainter than the sky. And then the sky itself, and then we're going to go back and go and observe it twice. Go do the sky once, go back, do the sky, do the object, the galaxy twice. But it's a little I mean, we can't see it, unlike with the other objects, we can't see it in the guider images at all. So we're just gonna do this for the next 6 hours.